Going to move on to chapter 11. This is our last calculus topic for the year, and then we'll be talking about some geometry related stuff. So the first topic we're going to talk about is the idea of the antiderivative. So for example, if I have like and I differentiate that, the result would be like 6x plus 4, right? And what we want to do then is find out a rule that would take 6x plus 4 back to 3x squared plus 4x plus 5. So in that sense, we could call 3x squared plus 4x plus 5 the antiderivative of 6x plus 4. So what we're really talking about right now is undoing the differentiation process. Is everybody okay there? What was the rule that we had for how to find the derivative of something? Okay. We had that, right? What we want down here is we're going to create a symbol to represent this derivative process. So the symbol we use is going to be that, where like this function is the function we're finding the antiderivative of. So the symbol before and at the end is just telling us to find the antiderivative. This is the integral symbol. That's the name we give that symbol. So what am I going to have to do to turn the 6x into 3x squared? Divide by 2 and add 1 to the exponent, right? So in general here, what we're going to be doing is we're going to add 1 to the exponent and divide by that new exponent. So for the 6x, that'll be 6 to the 6x to 1 plus 1 over 1 plus 1, or 6x squared over 2, or 3x squared, which is exactly what we want. So this rule right here is going to be what we'll use to find these antiderivatives. Everybody feel okay? And just like how if I wanted to take the derivative of 3x squared plus 4x plus 5, we can like distribute that derivative operation through and pull the coefficients out front. Right, where we can look at, we can do that kind of stuff. You guys remember that? It's a rule for derivatives. If we have that, if we're doing the antiderivative or taking the integral, it's going to work the same kind of way, where we can kind of like, distribute that integral symbol across, and we can pull coefficients out front. So the same rules that we use to kind of manipulate that derivative operation, we can use to manipulate that integral operation. Does that feel okay to you guys? Okay. Let's do some examples here. Oh, one other observation I should say. So one other observation. Let's say we have 3x squared plus 4x plus 2 this time. If I do the derivative of this, what are we going to get? Nobody can do the derivative of 3x squared plus 4x plus 2? Yeah, 6x plus 4. Which means then that if I do the integral of 6x plus 4, I should be getting that guy back again, right? Ruh-roh. Because before in our previous example, we saw that when we did the derivative of 3x squared plus 4x plus 5, that also is, oops, I was supposed to write a 5 there, 6x plus 4, which would tell us that the integral of that should also be 3x squared plus 4x plus 5. But Mr. It's just, we did the same thing. We're getting two different answers. That's not right. Something's wrong. Everybody agree? Right? You have the same input, but you're getting two different outputs. Do we like that to happen in mathematics? No. So what's the hitch here, Mr. Kulik? This constant at the end could be anything, right? Like you could have differentiated 3x squared plus 4x plus any real number at the end and gotten 6x plus 4. So if all we have is a 6x plus 4 to go from and we integrate that, we don't know what that constant at the end is going to be. So we're just going to write like a plus c at the end, because there are infinitely many answers that we could be getting. We call this guy the general antiderivative when we put the plus c on at the end. So whenever we ask for an antiderivative, we're really just asking to do our antidifferentiation rule and then add a plus c at the end. Let's do some examples. All right. I'll do a couple, and then I'm going to ask you guys to take over and help walk me through some of these. So we have the integral of 4t dt. So using my anti-differentiation rule that we just established, I'm going to add 1 to the exponent of my variable and then divide by that new exponent. And then plus c on at the end. Everybody feel okay with what I did there, formula-wise? Notice that I just kind of ignored the 4, right? So same idea. So that's just going to be x cubed, and then again, let's tack that plus c on at the end. What do you guys think? Not too bad, right? Let's skip forward maybe. Which one looks like a good one to do? Let's do E maybe. All right, probably don't need to do all of these. What's the antiderivative of 6x going to be? Right, because I can think about this as just doing that, right? So again, I'm going to add 1 to the exponent and divide by the new exponent. Now, what do I do with just a 2? Well, I'm going to think about 2 as like 2x to the 0, because x to the 0 is just 1, and 2 times 1 is still 2. So if I do that, I'm going to have 2x to the 0 plus 1 over 0 plus 1. And when I simplify this all down, I'll get 3x squared plus 2x, and then I need to put a c on at the end. Everybody feel pretty good so far? Going slow? Feels good? Okay. Let's do maybe h. I guess it's worth noting that, notice that like the dt at the end, it is a t because it's, t is the variable. If I use x for a variable, it'd be a dx. If I'm using n for a variable, it's dn. That just kind of declaring to you what the name of the variable is that we're in, or doing the derivative with respect to. Okay, so again, go ahead and do our rule. Everybody feel good about what I did there? So that's going to be -4. Oops, that's not supposed to be an x. We're doing n's. N to the -2 minus 5 over 2 n to the -1 plus 3n. And then tack on our plus c at the end. Yes, Carolyn. Okay, so what is your, tell me your hypothetical here.
So instead of writing -4n to the -2, -4 over n squared.
You could write as -4 over n squared. There's no problem doing that.
Okay, but do you like have to
Unless the directions tell you that they don't want negative exponents or something, either answer is acceptable. Yeah, it would be just a matter of like what the directions give you.
For the denominator from the 5n to the negative 2 plus 1, is that, like, how does that work? I don't know, does it go out to like negative 1 from the denominator?
Yeah, the denominator then is -1.
Oh, okay.
Oh, yeah, I'm sorry. Try it again, dummy. Thank you. Yeah, I did some bad arithmetic there. Oopsie-daisy. Thank you. One thing worth noting, if we go back to this rule, I'm going to put a little asterisk here. That rule works for all values of n except for n equals -1. So I can integrate a times x to the n for any value of n except for -1 using that rule. For -1, there's a different rule to use. You're not responsible for that one, but I want to point out to you that there's a different rule. Guess what it is? Guess what the antiderivative of x to the -1 is? You'll never guess. No. 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 It's the natural log of the absolute value of x. Yup. Would not have guessed it, right? Anyway, I needed to put that one point of clarification on. It just kind of came to me when we were doing that last problem. I'm like, I don't think they're going to run into something where, but I wanted to point that out to you because we're just being precise, you know? Yeah, Alyssa.
In the last example, so if you want like an exponent to the negative power for these ones, should it be not like the first term, would it be -4 like over 2 to the second power? Or
You could write it that way too. That is definitely fine. You could, you know. That answer is also perfectly fine. It would just be a matter of what the directions are asking you to do. If they indicate like, you know, write your answer with positive exponents or something like. But if there's no specifics on how they want your answer written, either answer is correct. I would accept either without prejudice, assuming the directions don't specify one versus another. Feel good? Okay. Let's do J. That's the last one. Can I integrate this the way this is currently written? No, because it's not of the form ax to the n, right? This is like a rational function rather than a power function. What do I need to do to get it to a place where I can integrate it? Yeah, I'm going to write it as two separate fractions with the common denominator of x to the fourth. Everybody's good there? If I reduce that first fraction, it becomes x to the -3. And the second fraction I can rewrite as 200 times x to the -4. Everybody feel good there? So that's the way I'm going to write this. So now I can do my regular old antiderivative rules. So I'm going to get x to the -2 over -2 minus 200 over 3 x to the negative 3. And then again, I need to tack a plus c on there. And if you wanted to, obviously you could write this with negative exponents, or with positive exponents, and just turn everything into fractions if you like. We don't need to, but you're welcome to do so. How do we feel here? Does this feel okay? Pretty easy? Same idea as before, just we're going backwards. Now, what if we're actually interested in finding a specific c here? What we're going to be doing, or what we're going to need, is some additional piece of information. So if you're given this additional piece of information about the value of the antiderivative at a specific point, or at a specific value of x, that's enough information for me to solve for c. Okay? So I'll start by writing my general antiderivative, which I know is just going to be the integral of the derivative, right? And I'm writing out a lot of work on these. As you get more comfortable, you can just kind of do these in your head, right? You can imagine a case where, just like when we did the derivatives, we start out by writing out me using the rule, and by the end you guys were doing them in your head. Again, you don't need to write it all out, but if you're ready to do it in your head, just start doing it in your head. So we know that f of x then is going to be x cubed plus 2x squared plus 5x plus c. And now, since I know that if I plug 1 in for f of x, I know that's equal to 6. So I can say that 6 is equal to 8 plus c. So c is negative 2. So we can say our final answer then is this guy. What do you guys think? No big deal, right? So if you get that additional piece of information, all that's telling you is that, okay, now I have enough information to solve for an actual value for c. I just do the antiderivative same way. Plug in the x, set it equal to the y, solve for the c. It's usually pretty straightforward. Christian? Sure. So we call this thing, your textbook calls this thing a boundary condition. I never really referred to it that way, but if you see that in the textbook, if you're looking at stuff, or if it's in the direction for a homework problem or whatever, that'll allow you to understand what it's asking for. All right. Who thinks they can walk me through doing example A? Somebody take a risk. Who's my risk taker here? Just let the pressure build and maybe somebody will finally buckle.
I'll try.
Yes! Go for it, Joey. All right. Yep, we want to find the antiderivative to start. So it would be what? Great. That sounds good. That looks good. So that'll simplify down to 25x squared plus 25x. Yeah, there we go. Excellent.
And then you plug the plug 1 is that. It would be 60 equals 25. 1 squared.
Wonderful. So C equals 10.
Yeah.
So our final answer we'll write is? Good. And we'll say f of x equals that stuff. And that looks great. What do you guys think? Totally doable? No big deal? Do we need to do the rest of the examples or we feel good? Okay. It's not too bad, right? Let's do kind of the same idea, but this time it's going to be like a story problem. I know these ones seem kind of scary. Okay, come on now. So whoever, the company that formatted this textbook, I want to fight because they consistently do stuff like this where they have a problem and then the parts of the problem run onto the next page and it drives me nuts. It's like, do something with your formatting to get these things to like, or just like put the whole problem on one page. You know, I don't mind like the solution, you're showing the solution that running onto multiple pages, that's fine. But it drives me nuts to be like, you read the problem and you flip the page to get to the parts and you're like, okay, what was that information? And you have to flip it, you know, it's like, this is just lazy editing. Anyway, the story says a factory has modeled the marginal cost of producing sunglasses as C prime of n equals 45n squared minus 130n plus 80, where C prime of n represents the additional cost in US dollars for an additional pair of sunglasses, and n is the current production level in thousands of sunglasses per month. The factory is currently producing 1,000 pairs of sunglasses per month at a cost of 50,000 US dollars. Write down the units for the antiderivative of Cn. Okay. So I know that C prime of n is in dollars per pair of glasses, right? So if we do the integral, the antiderivative of that, what unit will it be in? Let's think back to a scenario to help us. Remember when we talked about position, velocity, and acceleration, right? Position was measured in meters, velocity would be like meters per second, acceleration meters per second squared. And each of these was like a derivative of the other, right? Everybody feels okay there? So our antiderivative, which is take acceleration back to velocity, velocity back to position, but the units are still going to be the same units, right? So we are kind of living right here, and we want to end up over here because we're going the antiderivative route. So if we did from velocity back down to position, we went from meters per second to meters. In our problem, we're going from dollars per pair to dollars. Just dollars, the numerator. Does everybody feel okay with that? And if C is a cost function, since its derivative is the marginal cost, that should make sense, right? Cost function should be measured in dollars. Everybody's okay with that? So again, like when you take the derivative of something, you're going to get unit for y over unit for x. If you're integrating, you're going to just get the unit for, you're going to just get like, like the unit for y coming back. The only exception is like, if you go from acceleration to velocity, you're just losing like, like the y would be really meters per second, and the x, or the x is, the y is meters per second, and the x is per second. So you're losing the bottom of that still. It just, usually we don't write as meters per second per second. Okay. So that's part A. Everybody's okay with the analogy that I built to kind of show you why that works? In general, you should think about an integration as accumulation, right? Like if you're driving in your car at 50 miles per hour for 10 hours, you accumulate 50 miles of travel, 500 miles of travel. So like that's the equivalent of integrating a rate, gives you back a total. That's kind of what we're doing, just kind of an accumulation function. It says find a function Cn for the cost of thousands of dollars, or cost in the thousands of, find a function Cn for the cost in thousands of US dollars for producing N thousand sunglasses per month. Okay, so to do this, we're going to just take the antiderivative of this thing. So that's going to give me 5n cubed, 15n cubed minus 65n squared plus 80n. And I'm going to use d instead of plus c because I'm already using c for the name of the function. So I don't want to get confusing. So I'm just going to pick a different letter. Everybody's okay with D? Should we do K for constant, like we're in Germany or something? We use a K instead of a C? No? D's okay? All right. So I have this, but I need to solve for D still. Remember on this we have 1,000 pairs of glasses gives us costs 50,000 US dollars. So 1,000 pairs means that N is equal to 1, because remember, N is measured in thousands of sunglasses. And 50,000 tells us that C of N, well, let's say C of 1, maybe, is equal to 50, because remember, we said that C of N was measured in thousands of US dollars.
How do you know it's measured in thousands?
Because it says N is the current level of production in thousands of sunglasses per month. And it says that CN represents the additional cost in US dollars. But down here it says where does it say? Oh, CN for the cost in thousands of US dollars. So it told us in the problem, okay? So we then say 50 is equal to, and then we can plug our 1 in. So that's going to be 95 minus 65, so that's 30. And then, so D is 20. So our cost function then would be that guy there. Feels okay? Hardest part is just like making sure that you're keeping track of your units and what they're representing, because they're being kind of crummy here by giving you like N in thousands of units, and it's just like, that's annoying. And then at part C says find the minimum total production cost and the corresponding production level. So I am looking, if I read this question, I want the minimize for the cost. So I need to look at where C prime is equal to 0, right? Everybody agree? So again, C prime was 45n squared minus 130n plus 80 equal to 0. To solve this, I'm going to just use the quadratic formula. But I noticed that all my coefficients are also divisible by 5. That'll just make my arithmetic a little bit simpler. So let's do that first. So that's it's 9. Good gravy. N squared minus 130 divided by 5 is 12, 24, 26, I think. Plus, and then that is 16, I think. So plugging in to my quadratic formula. Somebody wants to double check my arithmetic there, I wouldn't mind, because I'm going to be quite honest, at 8:27 on a Thursday morning, I'm not so confident in my mental math skills to do double-digit divisions all willy-nilly, but I think I'm right. But if I was wrong, I wouldn't be shocked. You know what I mean? 26 squared. Who could do that? Geraldine, do 26 squared for me. 676. And then we're going to minus, hold on, I should be able to do this one in my head. That's 36 times 16. Let's just think about it as 8. Nope. Just do the whole arithmetic under that square root for me. 676 minus 4 times 9 times 16. What you got? 100? Spectacular. I love that because it's a perfect square. That makes life so much easier. So I have 36 over 18, which is 2. And then I'll have 16 over 18, which is like 8/9. So again, I could do either the first or second derivative test now to check these. I think I'm going to do the second derivative test and just plug these in if I'm trying to do this with no calculator. So like C double prime is going to just be 90n minus 130. C double prime of 2 is going to be greater than 0, 180 minus 130. C double prime of 8/9 is going to be less than 0. So this one is corresponding to my minimum. This one corresponds to my maximum. So n equals 2 is my minimum. That means like 2,000 sunglasses. And then my minimum cost, C of 2, I can just plug that into the answer that we got in part B. And when I do that, I get 40, which means that's like 40,000 smackaroos. Is that okay? What's the alternative that I could have done instead of like doing this to find the minimum and maximum? What do I graph? Could just graph C and use the minimum command on my calculator, right? No big deal there. You could do that also. Either way, it's kind of like doing the same thing. How do you feel on that? Other than like, ooh, it's kind of scary doing a story problem. Like words are hard. I get that. Well, let's do a little bit of 11-2 here, I guess, also. We'll just do a little bit of it. We're right here. It's not much of an extension. So what we're going to talk about here is something called the definite integral. In 11.1, we did stuff like this. Right? This guy is called an indefinite integral. In 11.2, we're going to do stuff like call this guy a definite integral. The only difference are these will have some numbers written here. These numbers are called the bounds of integration. The top number is called the upper bound, the lower number is called the lower bound. Shocking, I know. So let's look at doing this then in practice and showing you like, and really what this piece at the end means then is you're going to do like plug in the upper bound and then plug in the lower bound and subtract them. Everybody okay there? Let's do some numeric examples here. I don't like the way they typeset these either. Makes it hard to read what those bounds are. Okay, so let's say we want the integral from 0 to 2 of 3x squared dx. I'm going to start this the same way I have in the previous section. I'm just going to calculate the specific antiderivative. No plus c for definite integrals. I guess I should have written that up here. So that gives me then 3, it just becomes x cubed, right? So to do that, I'm just going to do 2 cubed minus 0 cubed, so I get 8. Notice that the answer to a definite integral is always going to be just a number, as opposed to the indefinite integral where the answer is a function. Let's do another, yeah? Okay. Let's do B. So we'll do the just general antiderivative here, regular old antiderivative. So that just turns into 14, oops, I guess t is the name of my variable here. So then to evaluate, I'm going to do 14t times, or 14 times 6 minus 14 times 3. I'm just plugging 6 in, and then I'm going to plug 3 in and subtract them. So that's going to give me 42. Feels okay? No big deal, right? Let's do one more, and then I'll show you how to do this particular thing on our calculator. Ooh. Okay. So again, I do my antiderivative. That's going to be 8/3 t cubed plus 5 over 2 t squared. Evaluate from 0 or from -1 to 2. I just did the antiderivative quickly in my head. You're okay at this point with me not writing down all the gobbledygocks. I think at this point we feel pretty good about doing that, right? Okay, so now we just plug in. Well, let's write it this way, I guess. So I plugged the 2 in and then subtracted it after I plugged the -1 in. Notice that that means I'm going to have to distribute that negative sign through, right? It's a very easy place to make an oopsie-daisy. So what do we get here? We got 64 over 3 plus 10 minus, well, plus 8/3 minus 5 over 2. So I guess I could get 72/3 plus 7.5, and just for arithmeticking here, I just stopped feeling like doing it. You know, this math is, numbers are hard in the morning. You know what I mean, guys? Oh, 72 over 3, that's a perfect, that reduces, right? Because 72 is 9 times 8, so that's just 16. Yeah, I can do it. 23 and a half. It's not 16. Yeah, it's 24. Thank you, 31.5. Cool. All right, so on your calculator, let's show you some calculator stuff here. So let's say I want to do the same problem that we just did on our calculator. Check this crap out. So I'm just going to turn my calculator on. I'm going to press the math button. I'm going to scroll down and pick command 9 called fnint. That stands for function integration. And all I have to do now is basically copy this down into my calculator, except I'm going to use x's instead of t's. So -1 to 2 of 8x squared plus 5x dx. Enter. Whammo! How rad is that?
You can only do it hands down.
Correct. But here's what we can do. If it is an indefinite integral, so say I was trying to decide, like, hey, did I do the, like the antiderivative right for this integral of 14 dt? Is it really 14t? Here's what I can do. If I go to the y equals, I'm going to type in math. I'm going to pick fnint. I'm going to go 0 to x 14 and then dx. And I thought the antiderivative of that was going to be 14x. Everybody's okay? I'm going to graph the two of them and see if I get the same curve. Oops. Before I do that, though, I'm going to go back and fix my window. Zoom standard. So there's my derivative. And I guess I should have picked a different shading for the line so you could have seen the 14t come through, but I only got one thing I can see, right? What does that mean? It did it like right over top of the other one, right? Here, let's do this. Make it easier to see. I'm going to do, okay. I'm going to do this option here where it's going to show the little cursor and then draw the line behind it. And then this one is just going to do the little cursor without drawing a line behind it, so you can see that it is going to follow the same thing. Now, the calculator is going to be slow graphing these integrals, but there's it drawing in the integral. And then I'll show you in a second. Then there's it drawing on the So I did this, is what I did. So you can do this, you can graph the integral to just check, right? And you can even do this if we're doing like these problems. Ooh, that's a lot harder. Let's not. You can check the antiderivative piece at least, right, without the plus c on there. You're gonna have to solve for c yourself. Won't check that well for you. Everybody's okay though? That's pretty nice, right? Thank you, Mr. Calculator. You're a very useful tool. Boy, I wish I had you when I was a calculus student 100 years ago. I mean, they existed, they just weren't commonplace. I don't think they had like the FN int and FN derive options, or if they did, it was probably a lot more cumbersome to use. All right, let's, what do we got left in here? Oh, I got one more example in this section. Sound pretty good to you guys? Okay. Keep in mind, because of the calculator with these definite integral problems, if the textbook directions say use your GDC to find the definite integral of blah, 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 it may give you something that you can't integrate by hand because it's just expecting you to type it into the calculator. Okay? So if you see something weird and you're like, I don't know how to do the antiderivative of that, if it says use your GDC to do it, you don't have to know how to do it, right? You just have to be able to get into the calculator and press enter and let the calculator handle it for you. Everybody's okay? I feel like that's a pretty good deal, right? You're like, okay. All right. So we'll do one more example. This one's another story problem. I know you guys hate these, so probably good to do it and talk through like what I'm noticing or what I'm reading when I read these to figure out the decoding piece, because that's always a challenge, right? It says a tank containing 10 cubic meters of water is draining. The water in the tank, or the water volume is given by, the change in water volume is given by dV dt equals yada, 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 where t is in minutes since the tank has started draining. Find the change in volume of water in the tank for the first 3 minutes. So we want to find out how much total volume has drained out of the tank, right? So in general, total is going to equal the integral of some rate. Everybody's okay with that? That's like our general accumulation idea. So we'll say that volume is going to equal the integral from 0 to 3 of dV dt. Guess how I'm going to do that? Doesn't tell me I have to do it by hand, so how am I going to do this? Yeah, I'm just going to let my old friend Kelky take care of this. 0 to 3, you're such a good friend, you've never let me down. You're always there for me unless you're out of batteries, and then I curse your name. Yes, sir.
How do you know if 3 is the bottom of the
Should usually always go small to big. And because it's the first 3 minutes, I know time should start at 0. So I get negative 0.4991, but we probably want to round that to 3 sig figs. So negative 1.50 meters cubed, i.e. the tank lost 1.5 cubic meters of water, right? If I get a negative volume that would mean that we lost some. So if we started at 10, how much did we lose? Or how much is in there now? Like 8.5, right? Cool. All right. Find the amount of water that drains in the time between 4 and 8 minutes. Okay, well, same idea. We'll just do that. So I get about 2 meters, right? Or 2 cubic meters. Feel good there? Okay. Uh-oh, somebody's coming. Hi,
Hi.
how are you?
Good, how are you?
Good.
This is casual for class for tomorrow.
Oh, great. Thank you. Don't forget your diapers. Or money. They'll take your money too. Colin's like, at diapers? I don't have any diapers. All right, it says find the time in which the tank will be empty. How am I going to do that? So I'm going to want to do that, right? Or doing it that way. Either is fine, right? Where you add 10 to both sides so it's equal to 0. Everybody feels good? Either way of thinking about it is okay. What I'm going to do is I'm just going to graph this integral into my calculator and find like the 0 or the intersection, depending if I set it equal to 0 by adding the 10 over, if we just have it equal to negative 10. I usually like it to equal 0 because it's easier for me to find a window. So we have the integral of, and then this thing, what is this thing's terrible function? It was something stupid. There it is. Look at all those zeros. That's like a counting problem. You know what Mr. Kulik's mistake he would make on this problem is? He'd miscount the number of zeros he typed in. That's what he would do. Oops. And I still have plus 10 at the end of that, though. So I'm going to do it with the 0 rather than with also typing in negative 10 and finding the intersection. But it doesn't matter. Both ways are fine. They work. They're doing the same thing. So I know after 3 minutes, we lost 1.5 meters. Between 4 and 8 minutes, we lost another 2 meters. I don't know how long this thing's going to take to drain. I'm going to hope by like, I don't know, 25 minutes or so, the thing will be empty though. After 8, it's going to be like almost half empty. So I think that's probably enough. Let's just hit graph. Here it comes graphing in. I set up the drawer so you can see the circles where the function is, where it's drawing it in. So I'm just looking for it to cross here, and then we'll use the 0 command to find that specific time. The only hitch with doing the integral on the calculator like this is it's slow. The graphing is slow. But I got a minute to sit here and wait to watch this thing do its thing. Oh, there it finished. Thank you. So I'll just do second and trace, 0 command, left bound, that looks good. Right bound, got to move that over. That looks good there. And then guess.
How do you get to the 0 command?
Second trace. And my numerical answer I get there is about 20.1 minutes. What do you guys feel? Feel okay on that? All right. Let's stop here. I think 2 sections in a day is plenty, right? So the homework for these sections are as follows. Here's the good news though, guys. Since we did the test on Tuesday and it's a 2-day week, guess what the problem set is for Sunday? Nothing! So 11-1 and 11-2 wouldn't be due until the following Sunday. Although with Irish Week next week, maybe you're better off trying to get it done so you don't have to like scramble to do that next week where you're like, oh, I'm so busy because I have to practice for the dance-off or whatever. You know, I don't know. I have to practice carrying an egg on a spoon so I can get 5 points. I have pillow fight practice after school for 6 hours. It's really intense. You know, I don't know.